He has started his new position as Assistant Professor in Center for Nanotechnology as IIT Roorkee since September 2024. He was awarded Plum Blossom Card and Taiwan Gold Card from Taiwan government. Now he is going to speak on Polymer Flexible Electronics with 2D materials. So please welcome with a round of applause.
Thank you for the introduction. Very good afternoon to everyone. First of all, I would like to thank Professor Mishra, the convener of this national conference, and also I would like to thank the co-convener, Professor Udit, for giving such a wonderful opportunity to show my research work here. So I'm going to talk about novel two-dimensional materials. Like we are using novel 2D materials and the PET substrates for a flexible optoelectronics. So before going to start, I would like to show some introduction. Like what is two-dimensional materials? I hope many of you are like well aware about the 2D materials, but I'm going to recall it once again here. Actually, it is a layered material which are weakly stacked together to form a three-dimensional structure. As we can see in the image, like atoms in the same plane have a strong interaction. However, between each sheets, there is a weak interaction. By some external force, we can easily cleave those weak bond and can separate into a single layers. So we can also assume in the other way that like a number of single playing cards are stacked together to form a bulk deck. From the deck, we can easily separate a single card. Likewise, from the bulk material, we can easily separate a single layer of material that is called two-dimensional material. So the best example is the graphene. This is the first two-dimensional material which was discovered from graphite. As all know, graphite, which we are using from our childhood through a pencil. But the two scientists viewed the graphite in a different perspective. They are able to exfoliate a single layer of graphite using a simple scotch tape exfoliation process. It's like peeling a thin slice of carrot using a peeler. So here they use a scotch tape to peel a single layer of a graphite called a graphene. So part of the groundbreaking achievement, like both scientists Andrew Game and Nasir was awarded Nobel Prize in Physics 2010. Since the discovery of graphene, there are tremendous development in the material science field due to exciting electrical and mechanical properties. But the application of graphene in the optoelectronics is very limited due to its zero band gap nature as well as poor absorption of light. So here comes the origin of other like novel two-dimensional materials which have optimum band gap in the range of like 1 to 2.5 electron volt, which is suits for the optoelectronic applications. Particularly, the transition is from direct to indirect or from indirect to direct. Depends on the thickness of the material. For example, in case of MOS2, it's called a molybdenum disulfide material. In the monolayer, it acts as a direct band gap nature. But in case of above monolayer, like more than one layer, it acts as a indirect band gap nature. And also, we can able to tune that band gap. In case of monolayer, the band gap will be 1.5 electron eV and act as a direct band gap. In case of bulk, the band gap is 1.2 eV. So based on the thickness, we can easily tune the optical properties of the two-dimensional materials. So theoretically, there are more than 1,000 2D materials were predicted, among which more than 100 2D materials were already produced. So the main aim of my research work is that to find a novel two-dimensional materials and use those 2D materials for the application, particularly in the transistors and photoreductor based applications. So how do we usually grow these two-dimensional materials? There are various techniques we can use to grow a two-dimensional materials. Like in case of the most commonly used material called chemical vapor transport, then bridgement techniques. Through this technique, we are able to grow a bulk single crystal, as you can see in the below image. So from the bulk crystals, with the help of exfoliation technique, by simple scotch tape exfoliation or by liquid exfoliation, we are able to exfoliate various kind of multi-layer, few layer and monolayered two-dimensional materials. We can also grow these two-dimensional materials directly, like monolayer material with the help of chemical vapor deposition or by physical vapor deposition. But we prefer the bulk synthesis. From the bulk synthesis, we exfoliate the monolayer. So as I said that, how we can do this by simple scotch tape exfoliation process. So like we take a small piece of bulk two-dimensional materials on a scotch tape and slightly start to rub on either end of the scotch tape. So as it has a van der Waals gap, so we can easily cleave those van der Waals gap. So we can separate into a various kind of layers, and finally we transfer into a various kind of substrate. So like for the flexible substrates, we are using here a PET, polyethylene terephthalate, for the flexible device applications. So for the first time, we identified indium selenide belong to a layered material, and we demonstrated a high performance and bendable photodetector on this indium selenide. So we grow a bulk indium selenide from which few layers were exfoliated with the help of scotch tape exfoliation. Then we transfer these exfoliated flakes onto various kind of substrates, like a silicon substrate and also a PET substrates. So when we interact with when we shine the light on the indium selenide, as indium selenide has a band gap in the range of 1.3 eV, so it can able to absorb your light and convert those light into electric. So as you can see, when light is shining on indium selenide, we are able to extract the basically we are converting the photon into the electron. So why you see we are able to get a good photodetector, and we try to demonstrate this device on the flexible substrate. So here we transfer this indium selenide on the PET substrate and try to shine a different kind of intensity of laser power, as you can see in the right side image. Then also we try to show a bendable and a planar state of our flexible device. So as you can see, even in case of flexible state, we are able to get a good photo responsivity. Responsivity generally is how much the efficiency of photon is converted into the electron. And also we demonstrated real-time measurements using this flexible device. So we are able to show a good performance even in the flexible state. Also, for the enhancement the performance of the flexible device, we try to grow various kind of other two-dimensional, previously we used the binary based materials, and here we grown ternary based, using three elements. Using three elements, we are able to grow various kind of two-dimensional materials. In this case, we have grown thin sulfoselenide, and in this case, we grown hafnium sulfoselenide. By this, we are able to show both kind of visible spectrum, visible based photodetector, as well as near infrared based photodetectors. So besides this, we also focusing on stacking various kind of two-dimensional materials, in order to get PN junction devices, as well as to enhance the performance of the devices, and also we need a broadband absorption, from visible to near infrared. So for that purpose, we are stacking various kind of two-dimensional materials. If you see the overall structure, it looks like the shape of you can assume a hamburger. So on the top and bottom we have a metal electrode, and in between we can stack various kind of two-dimensional materials. So how we can stack this kind of various kind of two-dimensional materials? Then again here, so here are some of the examples of our various 2D materials which were stacked on one another in order to create a PN junction devices. So how we can achieve this? Again with a PDMS polymer. So in this PDMS polymer, we are coated with PPC is another polymer. So based on this polymer, we are able to stamp various. We are exfoliating PDMS. Then using this PDMS, we are doing a stamping on the surface of one another 2D materials. So by this way, we are able to create multi 2D materials at one stage. In that, we are able to fabricate a device, and we can able to perform high performance both in case of visible as well as near infrared based photodetectors. And apart from that, very recently we are also focusing on the new kind of 2D family called 2D perovskites. So here it's a combination of inorganic and organic materials. So in this case, we grown butylamine formamodium based lead perovskite, and we are able to show this, even this 2D perovskite also can act as a flexible devices. So we transfer these 2D materials again on the flexible substrate, and we try to demonstrate good responsivity both in the planar state as well as bendable state. Yeah, thank you for the attention.